Hi. This video is going to begin our discussion of Unit 4, focused on the matrix inverse. By the end of this unit, you should be able to explain what we mean by the inverse of a square matrix. You should be able to explain the relationship between the singularity of a square matrix and the existence of a unique solution to a linear system. You should be able to explain the relationship between the elementary row operations involved in Gaussian elimination, elementary matrices, and the matrix inverse. You should be able to use Gauss-Jordan elimination to find the inverse of a matrix or to show that a matrix does not have an inverse. And you should be able to solve real-world problems with linear models using the matrix inverse. Our first discussion section is on a general introduction to what we mean by a matrix inverse, what its properties are, and why it's useful. So let's begin our discussion with identity matrices. If you remember, we can define a set of square identity matrices, one of every size. And these identity matrices have 1 for every element on the diagonal and zeros everywhere else. We can do this for a 2x2, a 3x3, a 4x4, or any size. We sometimes, when we need clarity on the size, we use a subscript to identify what size identity matrix we're working with, but we very often leave that subscript out when it's obvious from the problem or irrelevant to the problem what the size of the identity of that matrix is. One of the properties of the identity matrix is that when we multiply any matrix by the identity matrix of the right size, we get the same matrix back. So if we have an M by N matrix A, any M by N matrix A, if we multiply that matrix by the M-sized identity matrix on the left or by the N-sized identity matrix on the right, the answer is the same matrix I. When A is square, that means number of rows, number of columns matches. We don't really need to keep track of the size of identity matrix we're using, and we can simplify this as I times A equals A times I equals A for any n square matrix. This relationship is actually quite deep in terms of the formal concepts of mathematics, and we say that this IN, the n square identity matrix, is the multiplicative identity element of what we call a ring of all n squared matrices. We're not getting into algebraic theory here, but a ring is a sort of collection of mathematical objects that has an operation like addition and an operation like multiplication, and the I here is the element of that set that we apply multiplication and it doesn't change it. Right? The role that the identity matrix then plays in kind of this set of all square matrices of a certain size is very much analogous to the role that the number 1 plays in the analogous sets of numbers. Integers also form a ring in formal language. The rational numbers and the real numbers form what we call fields. Again, this is sort of moving beyond what we need to know for the course. But for all of these, whether we're dealing with a number that's in the set of integers, in the set of rational numbers, in the set of real numbers, or so on, 1 multiplied by a number equals that same number multiplied 1 equals the original number. Right? Exactly the same relationship as we have here for the identity matrix. Now, this relationship between, or similarity between the identity matrix as an identity element for matrix multiplication and the number 1 as the identity element for scalar multiplication leads us to think about a relationship for inverses, multiplicative inverses specifically. For real numbers, every real number other than 0 has a multiplicative inverse. That is, it's a number that we can multiply by to get the multiplicative identity, to get the number 1. Right? And so we can say that for any real number x, and the same thing will apply for rational numbers, and x not equal to 0, there exists some number that is also in the set of reals, or if we started with a rational number, a number that's in the set of rational numbers, such that if we multiply x and y, we get the same value as y and x, which is 1. There is a number that we can multiply by x that will give us 1. We define that number to be the inverse of x, which we sometimes, often for scalars, write as 1 over x. All right. Because the multiplicative inverse of a real number is also a real number, and of a rational number is also a rational number, it's actually this existence that makes the reals and the rational numbers a field as opposed to a different type of object. Integers, we can define a real multiplicative inverse for every integer, but that multiplicative inverse is not an integer. The inverse of 2 is a half. It's not an integer. Right? So this is our definition of what we mean by a multiplicative inverse for scalars. What would the multiplicative inverse of an n-square matrix be? Well, we might say something like this. Given some square n by n matrix, so a matrix A that is an n by n matrix, if we can find a matrix, to read this, it says, if there exists some matrix B that's also a square matrix, such that A times B equals B times A equals the identity, replacing the one with the identity here, then we might define B as being the inverse, the multiplicative inverse of A. Right? Now, this statement is just a definition that if given some A, if we could find such a thing, we would be able to call it an inverse. Now, there's some important questions that arise from this idea. For a given A, is there such a matrix? Right? Does this if there exists B statement become true? Can we find that? If we find a matrix such that A times B equals I, does that necessarily mean that B times A equals I? Remember that in general, matrix multiplication is not commutative. A times B does not equal B times A, so this doesn't necessarily hold true. If such a matrix exists, how can we find it? And does such a matrix exist for every square matrix? Does it exist for any square matrix? And so on. Right. Let's address each of these questions one by one. First of all, let's think about existence and uniqueness. We will explore some demonstrations of these ideas further on in the unit. But for now, let me just make a few statements. First of all, not all square matrices have an inverse. Some do, but some do not. Secondly, if a matrix does have an inverse, it is unique. So if there is a matrix that satisfies the rules of the matrix inverse for a given matrix, there is only that one. There aren't more than one. In the same way that the inverse of a scalar is unique. A couple points on language. If a square matrix does have an inverse, we sometimes say that it is invertible. We can invert it. We can find the inverse. Or we say that it is non-singular. Non-singular is the more common, more proper term. If a square matrix does not have an inverse, we say that it is non-invertible, or we say that it is singular. Very important thing to keep in mind is the opposite nature of singular and invertible. Non-singular means it is invertible, it has an inverse. Singular means it is non-invertible, it does not have an inverse. Okay. Now what about some properties of this? Again, I'm not going to really demonstrate these or prove these here. I'm going to leave these for the time being as a statement. If we have an n-square matrix A that is non-singular, so if if A is non-singular, then the following things hold true. First of all, A times A inverse does equal A inverse times A. They both equal, and both of products, of course, equal the identity matrix. This question of does the multiplication of A with A inverse commute? It does. This is actually an equivalent statement as saying that the inverse of the inverse of A inverse, gives us back our original matrix A. Right? So if we just think about this, if A inverse times A equals I, so A inverse must be the inverse of A, but A times A inverse also equals I, so A must be the inverse of A inverse. What also holds true is that the inverse of the transpose is simply the transpose of the inverse. This also obviously implies that the transpose of a non-singular matrix is also non-singular. If we have two matrices, A and B, which are both non-singular, then the product of those, either AB or BA, are also non-singular, and we can relate the inverse of the product to the product of the inverses. The inverse of AB is B inverse times A inverse. The inverse of BA is A inverse B inverse. Note that when we distribute the inverse through the product, we have to reverse the order of multiplication. And we'll see later on why this reverse of order is necessary. Keep in mind that in general, A times B does not equal B times A for square matrices. There are some exceptions, but most likely for a randomly selected non-singular A and non-singular B, the matrix multiplication will not commute, which means these two inverses are different things. Finally, if either A or B, or both of them, are non-singular, then the product AB and BA are also both singular. So these are some general properties of the matrix inverse. We will see why these are true, where these come from, as we start developing tools for computing matrix inverses and seeing where they come from. Okay. Now, We're now going to move on to one of the really interesting and essential results about matrix inverses and why they are important to us. Remember that a linear system of equations can always be written in a form AX equals B, where A is a coefficient matrix, X is a vector of variables, and B is our right-hand side vector of constants. When the number of equations is the same as the number of variables, then we have a square coefficient matrix. That also implies that X and B are the same length. And for square matrices, we can consider the possibility that A has an inverse. If A is square and has an inverse, then we can start with this AX equals B, and we can multiply both sides of this by A inverse. A inverse times A gives us the identity matrix, so I times X, which is just X. And on the right-hand side, we're left with A inverse times B, X equals A inverse times B. We have an answer for X in terms of the inverse and the right-hand side. The inverse gives us a solution just by multiplying by our right-hand side. Keep in mind in doing this, A here is the coefficient matrix, not the augmented matrix. It does not include the right-hand sides as part of it. Okay, so one of the really important things about the matrix inverse is its relationship to solutions to systems of linear equations. Let's talk about this a little bit more. So a square coefficient matrix implies that the number of equations, that is rows, is exactly equal to the number of variables, that is columns. And these kinds of systems very often have a single unique solution. And why is that? Well, let's think back to how we apply Gaussian elimination. If we go through Gaussian elimination, we'll have a unique solution as long as every pivot variable, or every variable is a pivot. When we have the equal number of variables and equations, what that means is that there are no zero rows in the coefficient matrix. So when we go through Gaussian elimination, there will be a unique solution unless Gaussian elimination creates a zero row in the coefficient matrix. This can only happen if one row is a linear combination of the others, and that's a less likely thing in general than it being linearly independent. Now, if we do have a zero row in the coefficient matrix, we can't have a unique solution. Whether we will have many solutions or no solutions will depend absolutely on the right-hand side. Remember, if we were going through Gaussian elimination in the augmented matrix, if we have a zero row in the coefficient block and a non-zero in the right-hand side, there's no solution. If we have a zero row in the coefficient block and a zero, that is just a row with no information. And in the case of a square matrix, if we have a zero row, we must also have a free variable, and so multiple solutions. So if we get a zero row in the coefficient block, we will either have many solutions or no solution, depending on the right-hand side. Corollary to that is that if we do get a unique solution for one right-hand side, that is if we go through Gaussian elimination and every variable is a pivot, thus we get a unique solution, then it will have a unique solution for every right-hand side. Again, these sort of rules are specific to square systems where the number of equations exactly matches the number of rows or variables. Right? Now, let's think about this a little bit. If the coefficient matrix is non-singular, right, that is, it has an inverse, we've just seen that we can find a solution for any right-hand side. The product A inverse times B will be well defined for any possible right-hand side, which means we will be able to find a solution for any possible right-hand side. But that means for a square system, the solution must be unique. Why? Because if we had a zero row, then many or no solutions would depend on the right-hand side. Some right-hand sides would give us no solution, some would give us many solutions. If we have a unique solution for one right-hand side, we have to have a unique solution for every right-hand side. And vice versa. So we have this relationship between non-singularity of a matrix and uniqueness of a solution. On the other hand, if the coefficient matrix is singular, then the system cannot have a unique solution. The system will either have no solution or many, depending on the right-hand side. We'll explore these ideas more as we get into actually trying to evaluate matrix inverses and so on. Okay. Now, we see there's a relationship between the ability to solve a system of linear equations and the inverse. But why is this particularly helpful? We already have a tool to solve linear systems, Gaussian elimination. What does the inverse give us that Gaussian elimination by itself doesn't? And I'm going to discuss two of the possible uses of the inverse. There are more places where the inverse becomes helpful, but this kind of starts to give you a feel for why the inverse is such an important thing. First of all, many applications involve a need to solve the same linear system, that is, the same system with the same coefficients with many, many different right-hand sides, or multiple different right-hand sides. That we might phrase in this way: A times X equals BI, where there's some set of different right-hand sides. Now, if we know what all of those right-hand sides are up front, we've actually seen this in a previous worked example video. We went through using Gaussian elimination to solve a system with two different right-hand sides at the same time. And we can use Gaussian elimination with a combined augmented matrix to do that. We can make a block of A, a block of B, B2, and so on. And we can carry through Gaussian elimination first to an upper triangular form with modified right-hand sides, and then through to our reduced row echelon form, which has essentially our solutions in that answer, at least if there's those last blocks, if there was a unique answer anyway. But this only works if we know what all the right-hand sides are at the same time. And this sort of application class, where we have the same linear system but with many different right-hand sides, often manifests in a way where we do not know all the right-hand sides at any time. As an example, think about an industrial production problem where we're trying to figure out production levels, hours run by various factories or various facilities, or amount of material processed by various facilities in the face of dynamic demand, that demands are changing. We don't know up front what the demand is going to be a year from now, 2 years from now, 10 years from now. The system may be the same. If you have the same set of facilities, that set of facilities is defined by the matrix A, the coefficients A. So we might solve for a production schedule for a set of demands, and that may either increase or decrease the next quarter. We want to adjust production targets based on that varying consumer demand, resolve the problem with a new set of demands. We didn't know what they were beforehand. We can't use this approach. We could recast the problem in and solve it through Gaussian elimination, but if A has an inverse, and we know that inverse, or we have found that inverse, once we have it, we can use that inverse to directly get the answer for any possible right-hand side, and this just involves matrix vector multiplication. When we go through later on the process of thinking about how we compute an inverse and how we apply Gaussian elimination, we will discover that matrix vector multiplication for big systems, imagine you have a system where A is 100 by 100 or 1,000 by 1,000, matrix vector multiplication is much, much cheaper than doing Gaussian elimination, much faster than doing Gaussian elimination. And so we have a quick way to solve the system repeatedly with any changes to the right-hand side. This is one place where the inverse becomes useful. Another application of the inverse involves thinking about how changes in the right-hand side lead to changes in the solution. Many applications involve uncertainty in some of the values of the problem. For example, again in the industrial production kind of problem, targets are often selected by predicted demands. Right? A company will decide the production schedules for a number of facilities based on what they expect the demand to be in the upcoming quarter. You're producing things for future sales, not for the past. Because these demands are predicted, there will always be some uncertainty there. And so we might ask the question, how would the solution be different if the right-hand side was different? If the predictions were off a little bit, a lot, or somewhere in between, how incorrect would our solutions be? How far away from the real predicted demands would our solutions land us? We might phrase this mathematically in the following way. If we have some AX equals B, a target set of demands, if we change the demand by some amount, we add some delta B onto our right-hand side, how would that change the answer? If we phrase the answer as x plus delta x, what is the change in the answer related to a change in a right-hand side? Right? If we have a small change in b, is the change in x also small? Or does a small change in b possibly lead to a very large change in x? In the latter case, we might be worried. We might set our production targets based on a predicted demand, but if the demand was off by even a little bit, our solution might give us our desired solution might be very different. Right? On the other hand, if a small change in B or even a larger change in B leads to a small change in X, we'd be very confident in using the production targets even though there might be even fairly significant uncertainty in demand. How does this play out with the matrix inverse? Well, this first system, if A has an inverse, if A is non-singular, then X equals A inverse B. Right? How would we solve this system? We would multiply both systems by A inverse. X plus delta X is A inverse times B plus delta B. We know, however, the rules of how we can distribute matrix multiplication into a sum. So this becomes A inverse times B plus A inverse times delta B. But A inverse B was our solution to the original system. So we see that x plus delta x is x plus A inverse delta B. In other words, delta x, the difference in the solution, is simply the inverse of A multiplied by the difference in the right-hand side. For a non-singular system, the matrix inverse transforms a difference in the right-hand side into a difference in the solution. This answers our desired question exactly. How does a change in the right-hand side lead to a change in the solution? And we see that it is the matrix inverse that defines that relationship. Okay. So what we've gone through in this video has been an introduction to what the matrix inverse is conceptually, some of its basic properties, and some of the reasons why we might be interested about it. In the next video, we will discuss how we can actually compute the matrix inverse, making connections between matrix inversion and Gaussian elimination. Thank you, and goodbye.